My favorite fruit in the world is ruby red grapefruit, which I actually call pampelmousse. So here I have a pampelmousse pendulum. I want to measure the period of oscillation of this pendulum, and what I mean by that is the time it takes for one complete oscillation, from one complete back and forth motion. So if we start from my right, go left and back to the right, that's one complete oscillation. So instead of measuring the period, I'm going to use a stopwatch and going to measure 10 periods. Why? Because my accuracy is not very high. I have a certain reaction time, that's a fraction of a second. This is a small pendulum, so the back and forth is pretty quick. And I had to estimate the end of an oscillation, which is precisely the time the velocity is 0, and it's not that easy to estimate in a small pendulum. Therefore, all of these errors add up and make my accuracy on the order of half a second to 1 second, which is not very good. So I measure 10 periods and then divide the result by 10 and divide the accuracy by 10, or the error by 10, which means that I'm going to have an error of approximately 0.1 second, which is great. Okay, so let's get started. I'm going to displace it, not start measuring right away. I'm going to wait one complete oscillation and then start my stopwatch. And that way I also improve my accuracy. So I displace, start 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 9.51 seconds. Do we think that this period is actually, or 1/10 of this period, which is, 9.5 seconds for 10 periods, so 0.95 seconds plus or minus 0.1. So I'm going to call this 1 second plus or minus 0.1 because that's my accuracy. So the period of oscillation of this particular pendulum is 1 second. Do we think that's going to change if we change mass? Let's see. Let's switch fruit. Let's go to a completely different fruit that weighs obviously a lot less. The mass of a cherry is much smaller than the mass of a pampelmousse, and see if that period of oscillation is the same. Again, I'm going to measure it 10 times and start the oscillation and start measuring after the first one. So 1, 2, 3, 4, 5. I didn't do this right. Let me try again. That's better. Okay, I'm gonna, when it goes to the right, now 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Precisely 10 seconds. So given my accuracy of approximately 1 second, this is 10 plus or minus 1 second. So the period of one oscillation is 1 second plus or minus 0.1 second. So to a very good approximation, these two pendulums have exactly the same frequency, the same period. Why? I went through great lengths, pun not intended, to make sure that the length of this pendulum is exactly the same in the two cases. The length of the pendulum is the distance between the center of mass of the pampelmousse or the cherry and the hook. So the effective length is not necessarily the length of the string. See here, there's a stem for this cherry. The pampelmousse is obviously much larger, but the centers of mass of the pampelmousse and the cherry were exactly the same distance from the hook. So the effective length of the pendulum was exactly the same. This is why the mass didn't matter. The only thing that matters is the effective length, and that's why the frequency was the same, the period was the same for the two. And now, the best part. Yum.